I audible? Can someone tell me? So can you check once again? My voice is clear or not?
So I think am I audible now? So as a part of that PMRF work, I need to take additional sessions outside the research work. So I will take on every Monday 7 p.m. to 9 p.m. Okay. So what we will do during this session, we will quickly go through the concepts which is covered during that particular week. We will solve some previous year question and assignments, and then we will open for the question and answers sessions. So although throughout this session the chat is open for your question answers, and after each sessions you will get the link to the video records and some materials which I will provide. So this course is all about design of steel structure, right? So before going to the design part, the code requirement part, first let's try to understand what do we mean by say steel structures, why we need the steel structures, what are the difference of the steel structure rather compared to its alternatives. So here we have a RCC structure, okay, and a steel structure. So let's try to differentiate this structure. First of all, what comes in our mind? The difference based on the material. So this is made from RCC, this is made from steel. So I will come into the material part little later. First, try to understand what is the difference uh, with respect to a structural engineer or with respect to a execution engineer. Okay. So for a with a view of structural engineer, let's try to find it out. So to construct this RCC structure as a structural engineer, what we need to do? First, we need to design all the elements. Elements means the beams, the slab behind it, the columns, and the foundation which is below the ground. So we need to design all the elements. Now as a execution engineer or as a site engineer, what he or she has to do? He or she has to construct from the bottom first foundation, then curate, then the column, and successively the story we will construct. Now let's try to find out what happened in case of steel structure. So in steel structure, these elements, or we call them structural steel elements. So these structural steel elements are readily available. We just need to pick them based on their or based on our load and serviceability requirements, and then we need to connect them. So as a design engineer, we need to more focus on the design of the connections, right? We don't need to design that sections and all these things. So first, yes, we have find out some differences with respect to or with the perspective of a design engineer. Now, let find it out some difference with respect to a site civil engineer, site execution engineer. So for the execution engineer, what he or she need to do? He or she need to construct, cure all these elements for the RCC structure. But for the steel structure, he or she need to ensure that the connections are, happening whatever prescribed in the design. So one thing that come into notice, that speed of construction. So speed of construction in RCC structure is slower than the steel structure, because we don't need to cast the elements, we don't need to cure the elements, just make the connection happen. Yes. Secondly, with respect to the site engineer, as we need to cast these all elements on site, but these elements are cast on factory in a constant environment. So there is less probability of compromise with the quality. So better quality control. So yes, now we have some sort of ideas that why we should go for the steel structure. So firstly, speed of erection, quality control. Now come to that you know material perspective. So firstly, RCC and steel. This is made from steel and this is made from RCC. So we all know that steel is more ductile than RCC. Ductile, what do you mean by say ductility? So ductility we'll cover it in later slides in detail. But for now, ductility, we call it, is the property of material by virtue of which a material can withstand a higher amount of deformation, permanent deformation before failure occur. That means it can elongate more before failure occurs. So for this ductile property, what we get? We get that steel structures, we can make it more ductile. And more ductile structure, we can avoid the catastrophic failures, right? One more thing, steel. What do you know about steel? In steel, the strength to weight ratio is more as compared to RCC. That means eventually our dead load will reduce and we can have much safer section, or we can put much load on the sections, right? So now, yes, we have some ideas why we need to study that subject, why and what sort of things we need to do in the subject design of steel structure with respect to design engineer and with respect to the structural engineer. Now come to the code part. So for the designing, we need some sort of codes. Like first and foremost, the code is IS 800, which covers the limit state design part. If we want working state design, we need IS 800 1984. Now one handbook where the steel section specifications are provided. Now steel table for the loads we have IS 875. So I will do one thing. I will upload all these codes in the Google Drive folder so that you can download, and if you want you can print them, right? Okay. So yes, till now we have a essence, what we are going to do in design of steel structure. So design of steel structure, about the steel structure, what do we knew? The steel structure have some sort of advantages and it has some sort of disadvantages. Like it has, we already have discussed, it has high strength to weight ratio. That means we can get better strength out of the material and the dead load will relatively small. Ductile property, we avoid the catastrophic failure. The speed of erection, will eventually reduce the cost of your construction. Quality of construction, already I said, ease of repair, all these things. And this has some disadvantage like fireproofing. It has a great disadvantage with fireproofing it, or the fire resistance. Then we need skilled people to make the structure happen, which will increase the general cost of the some projects. Then buckling, I said that high strength to weight ratio, that means the sections are becoming slender. That means the lateral dimension is less, so there is a chance of buckling. So these are sort of advantages and disadvantages of the steel structure. Now let's quickly come to this portion. I already told you that steel structures are made from the structural steel sections. Now what we and I also said that these structural steel sections are readily available. So let's try to understand which kind of structural steel sections are available and what are their specifications, right? So first we have rolled section, or rolled I section, or we call it beam section. So all the specification of this beam sections is given in SP61. I will come into SP6. Okay. So In sp6 we have generally 5 series of beam sections, and these beam sections like Indian standard junior beam sections, Indian standard lightweight beam section, Indian standard medium weight beam section, Indian standard heavyweight beam section. We have one more, you know, beam sections here that we call, wide flange. So first, let's try to understand how these beam sections are designated. These beam sections are designated by a number followed by some, uh, weight. Say for example, 35 kg per meter cube. So ISMB 400 means it's an Indian standard medium weight beam section whose depth whose depth is 400 mm. Okay. Likewise, if we have IS, say for example, HB 500, that means it's an Indian standard heavyweight beam section whose depth is 500 mm. Okay. Now, as I said, these all the specifications or the properties are given in SP6. So here SP6 table 1, these are for rolled beam sections. Say for example, we need to find out the properties of the ISLB 100. So we have all the properties like weight per meter, what should be the weight per meter, what should be the sectional area, what should be the depth of the section, what should be the flange width, and all these moment of inertia, radius of gyration, and also here on that right side there is a page where other specifications are given. So these specifications are already or readily available in our code. Now, like beam sections, so generally beam sections are used in for making beams, columns, etc. Now we have channel section, rolled steel channel section. Why you call rolled this section? Why we call this section rolled sections? Because these are made from, melting them and pouring in a formwork, and we make the structure. So as per our handbook, we have 4 series of channel section like Indian standard junior weight channel section, lightweight channel section, medium weight, and standard weight. Also, these channel sections are designated by some number. So this number is called, say, ISLC. That means it's a lightweight channel section or light channel section whose depth is 400 mm. Like channel sections, we have angle sections. Angle sections basically angle sections basically have 2 legs, right? Here, this is one leg and this is another leg. So one leg is connected to some sort of member or gusset. Say for example, if we want to connect this leg with a gusset. So what will we do? So for example, we have a gusset here and we need to connect the plate, connect this using gusset. So what do we do? We will make holes here. We will put the bolt over here and make the connection happen. So here for the angle section, we have 2 legs. The one leg which is connected to gusset or some sort of members, we call this leg as connected leg. And the leg which is not connected or some load is applied from here or through here, we call this as, what do you call it, as outstanding leg. Okay, so the Indian standard equal and unequal sections we divide into 2 parts: Indian standard equal angle sections and one is Indian standard unequal angle sections. Okay, so in equal angle sections, these 2 legs, the length of these 2 legs are same. Like ISA 14 to 14 to 6, that means the width of this leg is 40 mm, width of this leg is 40 mm, and the thickness is 6 mm. Likewise, unequal angle section, that means, say for example, I have an unequal angle section of 40 into 25 into 6. That means the width of my connected leg is 40 mm, width of my outstanding leg is 30 mm, and the thickness is 6 mm. Generally, the unequal sections are more preferable in designing the tension member. Likewise, we have T sections. These T sections are also designated by its depth. And lastly, we have two, uh, you know, important rolled sections. Like one is Indian standard bar section, Indian standard round section. So round bars are designated at ISRO, Indian standard round sections, and the square are designated by Indian standard square sections. So what does that means? ISRO 100. That means that we have a Indian standard round section. We have a Indian standard round section of diameter 100 mm. Similarly, for square bars like ISSQ 80 will mean we have a square bar whose each side is 80 mm. Okay. So from this we can understand what this ISRO Indian Standard Round section and what this IS is Indian Standard Square sections mean. Now we have three more sections. Here we have another more sections. I will complete. So we have seat and strip sections. So Indian Standard Steel seat sections, that's seat sections, and Indian Standard Strip sections. Seat sections SH, ST. So here all the specification of these seat and strip sections are provided in IS 1730. So this is the screenshot of this section. So here we can see the seat shall be designated at ISSH, followed by its length, width, and thickness. Now ISST, what does that portion mean? That means it's a strip section, and for the strip section only we need to provide the width and thickness. So what we can understand, the seat sections, while we need to specify the length for the bigger sections, larger sections. So for this kind of sections we need to specify that how to design the sections, and how to specify more precisely we call it how to specify these sections. We have one more sections, that is we call ISF, Indian Standard Flat Plates. So this is generally denoted by ISF, say for example 200 into 10. That means we have a Indian Standard Flat Plate section of width 200 mm and whose thickness is 10 mm. Say 100 लिख दिया, इसको हटा दो 10 mm. Okay. So there are three kind of strip and seat sections. One is Indian Standard Flat Plate sections. One is Indian Standard Strip section, ST, designated by ST. Don't mix up with the seat section. So here all these things are mentioned. So in seat sections, length, width, and diameter thickness is specified. For the seat sections, we have what do we have? We have the width and thickness, and for the flat plates, we have the width and thickness only. So now, for up to now, what we get or what we try to understand about the steel structure, that yes, steel structures are made from steel, and there are some elements which we call the structural steel element. These steel elements are readily available. We can using this, we have to make a building, a steel building. As a designer, more precisely, we have to focus on the connection part. So we'll go to the connection little later. First, let's try to understand the material properties of the steel. Okay. Now is it visible and audible? Can someone confirm? Okay. So yeah, yeah. Thank you. So let's come to the topic. So till now, what we have understood about the steel structure, that in steel structure As a design engineer, we need to more focus on the connections rather on the elements. Secondly, we have some idea about the material, not full idea, so I will go into that. And we have some idea that there is some members are there and their specifications, from where we can get the specifications, all these things we come across. Now it's steel, right? It's a steel building, so we need to know more about steels. We know about the structural elements, that beam elements, angle sections, eye sections, channel sections, all the sections are there. Now we will understand later that how to play with these sections and how to connect them to make a structure, right? Okay, so let's quickly go through some properties of steel, because we are dealing with the steel, right? So let's quickly go to some basic properties. Like, first we will go to the physical properties. That means the inherent properties of the steel material. So we have first the unit mass. We all know that unit mass 7850 kg per meter cube. Unit weight 78.50 kilonewton per meter cube. Now modulus of elasticity. Uh, Tell me, what do you mean by say modulus of elasticity? Yeah, give me some answer. What do you mean by say modulus of elasticity? Write it down quickly. What do you mean by say modulus of elasticity? Yeah, try it. You have already studied. So give me a perfect definition of the modulus of elasticity. Okay. So let me quickly try it. Okay. So first, let me clear some basics. Okay, basics from your strength of material. So for example, first try from the basics. So first of all, let's try to have a section. Okay. So it's a, say for example, it's a prismatic bar. So first we need to find out its axes. So first do the coordinates. So say for example, this is x, this is y, this is z axis. Okay. So first of all, tell me which axis we call the longitudinal axis. The axis with respect to the length we call the longitudinal axis. So this is your longitudinal axis. Okay. Now, what do you mean by say cross section? So these terms or terminologies we very often encounter this. So what do we mean by say cross section? So the section perpendicular to your longitudinal axis. The sections perpendicular to your longitudinal axis are called the cross sections. Okay. Now, what do we mean by say transverse axis? The axes which are perpendicular to your longitudinal axis are known as your transverse axes. Okay. Now, modulus of elasticity. What is the definition of the modulus of elasticity? I asked. It is the ratio of normal stress to normal strain. Now I use that terminology normal. Now what do you mean by say normal stress and normal strain or shear stress? So the stresses and the forces which are acting perpendicular to the cross section, which are acting perpendicular to the cross section or which are acting parallel to the longitudinal axis, known as the normal forces slash normal stresses. If we know the forces, we can calculate the stresses. We know the cross-section area. Okay. Now, secondly, what we call the shear stresses. So the stresses or forces which are acting transverse towards this cross-sectional area or perpendicular to the longitudinal axis. So it may come from this transverse axis, it may come from this, or it may come from this. These all the forces and loads which are coming or which are acting, more precisely, which are acting perpendicular or in the transverse direction, not perpendicular, sorry, in the transverse direction of the cross section or perpendicular to the longitudinal axis, we call them the shear forces or the shear stresses. So modulus of elasticity, what do we know? It's the ratio of the normal stress to the normal strain up to the proportional limit. Okay. So modulus of elasticity of steel we know 2 into 10 to the power 5. So that will be 10 to the power 5, not 105. Then Poisson ratio. What do we mean by say Poisson ratio? It is the ratio of two strength, lateral and longitudinal strength. So it's zero point 0.3 and modulus of rigidity. Now that modulus of rigidity comes play. So it's the ratio of shear stress upon shear strain. Okay, so these are the basic difference between the modulus of elasticity and modulus of rigidity. So now you understood very well that what do we mean by say normal stresses, what do we mean by say shear stresses, because during this whole class or whole session we will very often use this kind of terminologies. Okay, so this is the basic part. Now come to some mechanical properties of the steel. Now what we call the mechanical properties of the steel, किसे हम mechanical properties बोलेंगे, the properties which we can derive from the or we can obtain or we can observe from the application of external loads or stresses, we call them the mechanical properties of the material. So first mechanical property is the strength. Now what do we mean by say strength? What do we mean by say strength? Strength is the value of the maximum stress which one material can withstand before failure occur. Or more precisely, if we say, it is the value of maximum stress which a material can sustain without failure. Okay. So now it's the maximum value of stress. So for steel, we need to consider two kind of stresses. One is yield, one is ultimate. Now why these things we consider the two stresses, why not the others, or more precisely why we go for these two strengths? So I will come into it when we study the failure criteria of the steel members. Okay, so first thing, this is the strength where we consider the yield stress of the steel, and you all know what is the yield stress or the ultimate stresses. These are the basic from the song. Till now, still I will cover that, go through this concept once again. Now ultimate, why these things happens. So when we go through that philosophy, design philosophy, then we come to know that what are the main points to considering the stresses. Now secondly, ductility. We have already discussed in the first slide when we are try to understand why we go for the steel structure. There I said that it is defined as the property of a material by virtue of which it can undergo large deformation. So ductile material किसको बोलते हैं हम लोग? Ductile material जिसका post elastic strain is more than 5%. Okay, post elastic strain beyond the elastic limit, that means it can withstand the permanent deformation. Beyond the elastic limit, post elastic means beyond the elastic limit strain. Okay, so tell me one thing. So if I have, so this is a mild steel curve, and if we have say some cold work bars, so Fe410, and this is a Fe250, and this is Fe410. So now tell me, uh, between these two, which one is more ductile? Which one is more ductile? So it will fail somewhere here, and it will go up to this cracking. So tell me, which one will be more ductile? Tell me, which one will be more ductile? Yeah, Fe250, because we have more post elastic strain, in case of the mild steel section. Here we have seen that Fe410 have failed here. So with respect to the ductility, we can say that that property will help us or help the designer to ensure the safety against the catastrophic failure. Okay, so for example, like which one is more ductile, rubber or Fe250? Obviously Fe250, because Fe250 has more post elastic strain than rubber. So then ductile material, we can categorize it into like purely ductile, intermediate ductile, less ductile. So 5 to 15% is purely ductile, less than 5% it's rigid material. So these all things are covered in your strength of material classes. So I will not go details into that. Now, what else the properties like toughness? Yes, it's a good property. So by this property, one material can withstand the effect of impact loading. Impact loading. Okay. So we can define this property like that. One material can absorb the maximum energy before failure. Or we can say this toughness, we can measure, we can call it like it's the strain energy per unit volume. It's a measure of strain energy per unit volume. Measure of strain energy per unit volume. So how we can calculate the toughness? If we have stress strain curve, how we can calculate the toughness? The area under this stress strain curve will give us the value of toughness or the total energy which can absorb by this material before failure occurs. That means if we now think about it, like this is Fe250 and this is Fe410. So which one is more tough? Yes, Fe250, because it can absorb more energy than Fe410 before failure occurs. Now hardness doesn't necessarily means that it's hard. It's the property by virtue of which some material can, resist the indentation and crashing. Fatigue, obviously, fatigue comes into play when that repeated loading or the cyclic loading is there. So for the fatigue loads, uh, when we study that strength of material, we come across that terminology that uh, you know up to that limit, if we repeatedly use that strain, then that will not fail. So some tolerance limit with respect to fatigue we set, and from SN curve we will calculate the fatigue strain. So these are some basic properties of steel. As we are dealing with the steel structures, we have to know about the steel and about the properties of the steel material. So these all are some kind of you know short um, takeaways of the mechanical properties of the structural steel. So when we will design that, we will come these properties, or we will go through these properties if we need them. So we'll in details we will go through these properties. So basically, we have different kind of steels, like based on carbon content. We have carbon steel, we have high carbon steel, and we have stainless steel. So in stainless steel, we have nickel and chromium. These two foreign material we have add to that. And now let me explain one vital concept. Like with carbon content, if we increase the carbon content, generally what is the carbon content for the steel? Tell me. Generally, what is the carbon content for the steel? Write it down. What is the carbon content? Basic carbon content. Generally, it's vary from 0.2, right? So if we increase the carbon content, what will happen? If we increase the carbon content, what will happen? Strength will increase. Strength will increase, but eventually the ductility will decrease. Ductility will decrease. So if we want the ductile property and strength at the same time, so we have to very cautious about selection of that carbon content. Okay. Now, so till now, what we have learned about steel structure. First, we have understand why we go for the design of steel structure. What is the need of studying this subject? So now we have some essence, like yes, steel structure have some advantages. In steel structure, uh, we come to know that how to design them in a short idea. Like we just need to design the connections. We have some elements, we need to select the elements, and their elements are made from steels. We come across the steel. Now to design anything, what we need a method or a philosophy to follow, right? So how to choose that method and philosophy? So, so till now, do you have any queries or questions? You can put it in the chat box. Okay. So now, design philosophies. So our code IS 800 2007 that includes the limit state method of philosophy. Now design philosophy. While designing the RCC, we came across the different design philosophies like working state method, ultimate load method, and finally the limit state method. So in 2000, IS 800 2007, that code solely refers the limit state method of design. If we need to go for the WSM or working state method design, we have to go for IS 800 1984. And these codes also don't cover the working state part, so we will directly go into the limit state method of design. So in limit state method of design, what we generally do, we actually underestimate the material strength. So generally we underestimate the material strength and overestimate the loads. Now I will come into it. So in limit state method of design, we all know from the basics that we introduce two kind of factor of safeties. One, factor of safety for material. One, factor of safety for loads. So by the introducing that factor of safety, what we are doing in that philosophy, let's try to understand. We just underestimated the value of strength. Like if some material have the characteristic strength, say for example, if some material has the characteristic strength is 20 MPa, and my factor of safety for the material with respect to limit state method say is 1.5. So what will be my design strength for this material? So the design strength will be Ft equals to FCR, characteristic strength or the ultimate strength, divided by gamma m. That means introducing that factor of safety, we are underestimating the material strength. That means if some material can withstand higher amount of load, still we are assuming that that material can withstand only that amount of load. Now, for the loads, what will we do? Remember from your RCC, say we have dead load and live load combination. So we put some factor of safety over here. That means our design load, say design load is equals to this. So if my combination of live load and dead load is 100 kilonewton, but we will design with respect to 150 kilonewton. So what will happen? By this process, the structure will be more safe. So we ensure the safety factor with respect to the material. We ensure the safety factor with respect to the loads. So now you can understand why I said we underestimate the material strength and overestimate the loads. Now come to what we call the limit state. So we all know that limit state is the acceptable limit of safety and serviceability requirement. Now safety and serviceability, most important thing with respect to a design engineer, what we need to do. So if you need to design something, what you have to consider first 2 or 3 factors. Tell me first 2 or 3 factors that we need to consider during this design process. First, we need to ensure the safety. Yeah, first thing, we need to ensure the safety. Secondly, we need to ensure the serviceability. Thirdly, we need to ensure the economy also. ऐसा डिजाइन दे दिया जिसमें पैसा बहुत लग रहा है, so client will not accept that. Okay, so these 3 things we need to very clear while designing. So safety, that comes under the limit state of strength or ultimate limit state. So basically the limit state philosophy is divided into 2 parts. One part cater the strength, safety, that part. So more precisely the safety part. And secondly, what do we mean by say serviceability? So safety, we know what do we mean by say safety with respect to some design. Safety means the building should not overturn, the building should not collapse, the building should not buckle during its service period. Now, what is the serviceability? That requirement comes due to the occupancy level. That means if I design a building for residential purpose and I make it a flexible structure, so what will happen? The building will vibrate. What will happen? Excessive vibration will cause that discomfort to the occupancy or the people who are reside there. So serviceability, and at a time we need to ensure the economy. So for the design philosophies regarding limit state of design, we have two kind of limit state. One is ultimate limit state and one is serviceability limit state. Now, our IS 800 2007 that covers ultimate limit state or includes the ultimate limit state as loss of equilibrium, loss of stability of structure. That means loss of equilibrium of a structure as a whole and as a part. Now, as a whole and as a part, this concept I will cover it. Okay, that actually comes from the reliability analysis of the structures. I will go into it little later. Now, failure due to excessive deformation, cracking, brittle failure, and under the serviceability limit state, our code covers excessive deflection, excessive vibration, fire resistance, crack width, etc. So we have two limit states, right? Think when we have designed the RCC structure, we have only designed with respect to the ultimate limit state. But the serviceable limit state also come into play when there may be excessive vibration, maybe excessive deformation or excessive deflection. So for these conditions, basically, we need to you know uh, consider this serviceability limit state. Now we are dealing with the limit state method of design. The limit state method of design. Obviously, there is a partial factor of safety. Now, the thing is, I always wonder from where these magic numbers are coming from, like factor of safety 1.5 for the material or 1.5 for the loads. From where our codes get that informations, right? So this information is actually coming from the reliability analysis, where capacity and demand comes into play and the randomness of the loads. So there is a subject called structural reliability. So there, through the reliability analysis, first we find out some um, reliability index. So we call them reliability index instead of calling them you know uh, factor of safety. Okay, so let's quickly cover which kind of factor of safeties we have to deal with in steel design. So firstly, now I already told you that we have to consider two strength, F, Y, the yield strength, and Fu, the ultimate strength. Why these two strengths are considered here? Now, consider one thing. Say, for example, let's try with a plate, solid steel plate. So it's a solid steel plate. Now I am applying the load, P, P. Applying the load, my intention is to, fail the section. Okay, so I will apply, increasing the load. So what will happen? This will get first elongated, then some fracture will happen like this. First elongation will happen. This bar will elongate. Then sometimes it will crack and break apart. So now we have understand we need to consider the serviceability limit state and ultimate limit state. So if there is excessive elongations, this stage we also call it a failure. So for a solid plate, if there is a solid plate, this tendency of rupture is you know more likely less happening phenomena. Rather, if we have a member like this where we have made some holes, now we are applying this load. So here what will happen? The rupture will happen first before yielding. So we have to consider that Fy yielding as a failure for the cross sections, while there is no holes and all these things mechanism. That means where we don't reduce that cross sectional area. Secondly, the rupture. Now, when this rupture will happen? Rupture will happen only this material will cross its ultimate strength. So we have to consider the two strengths of failure. One is yielding as a failure for the solid members. Then we need to consider the ultimate load or ultimate strength as a failure for the member where we have made some holes. Why we need that holes? Because we will eventually make the connections with bolts, rivets, all these things. So here now you can understand the partial safety factor for material. So here you can see resistance governed by yielding. So when we are considering the yielding part, the factor of safety should be 1.1. When we are considering the ultimate stress, the factor of safety should be 1.25. Now for bolt and rivets, the factor of safeties are given. So when we will cover that bolt and bolt part, we will revisit that table. This is table 5 of your IS 800 2007. So we'll revisit that again. So now you have idea that in steel we consider two stages as a failure. First, the yielding, and secondly, the rupture. So these two conditions will come when we will design a section or we will come to arrange a bolted joints. So these things will get clear. Now for the loads, I have already said for the loads, we have overestimated the loads. That means we introduce a factor, partial factor of safety. So design load equals to some factor of safety gamma load into your load combination. What will be your load combinations? So we overestimate the load. Now, what do we mean by say characteristic load or characteristic strength? That means the load or the strength which will not exceed the probability of failure 5%. Or what we can say, what we mean by say characteristic compressive strength of concrete. What our code says it is the strength below which not more than 5% of the test results are expected to fall. That means we are not allowing the failure probability more than 5%. Okay, so as I said, when we will design the sections, we will revisit these two tables again and again because we need these tables more often. Okay, so till now what we learned about or what we get um, mm, or come to know about this design of steel structure. First, that these buildings are or these structures are made from steels. These structures are made from some or structural steel elements whose specifications and all these things are given or provided, so we don't need to design them one by one. Thirdly, we have a design philosophy by which we can make the connection happen. Okay. So now come to the connections, the most important part. As a structural designer or as a structural engineer, what we need to do with that steel structure is basically we need to design the connections. We need to design the connections. So there can be different kind of connections like beam column connections, beam to beam connections, beam to gusset connection, purlin connection, in truss member there may be connections. So there may be uh, different combination and different kind of connections. Now the main question, how to connect them? What should be the method of fabrication by which fastener we can fasten that members? So basically we have three kind of fabrication method and three kind of joints actually. So firstly, riveted joint. What do we mean by say riveted joint? These joints are made from rivets. Okay, I will come into it. Now, bolted joints. So these joints are you know made from the bolts. That means here you can see column to beam connections, and this column beam is connected through the bolts. So the connections which are made from the bolt or the connections where bolt is used as a fastener, we can call them bolted joint. Similarly, rivet for the riveted case where we can consider the rivet as a fastener, so we can call them riveted joint. And one more thing, we have welded joints where the structural members are joined or connected through welding. So we will during this course we will learn how to design this type of connections, how to deal with this kinds of connections, and what are the possible sort of connections. So we will go through it one by one. So now we have, yes, we have uh, some idea about the connection, how to connect the structural elements to make the building or make the structure happen. So first, riveted joints. So our code IS 800 2007 don't include the design of rivet connection. So if someone want to uh, visit the clauses and criteria of the rivet joint, uh, we have to download the code IS 800 1984. Okay, so I will do one thing. I will upload all the codes which will be required for this design of RC structure in the Google Drive, and this link will be shared by the NPTEL support team. Okay, so from there you can directly download these codes. Okay, so let's come to the riveted joint. First and foremost, connections which comes in our mind when we will try to connect two members. So riveted connections. So in riveted connection or rivet connection, the rivet is mainly used to connect the members or connect the structural elements. So first let's try to understand what we call a rivet. So riveted looks like this. It has a head portion and a body which we call shank. So rivets does not have the thread like which bolts have. Rivet doesn't have. So rivet have two portions. One is head. So this diameter is called the head diameter, and this diameter is called the shank diameter. Shank diameter, and this diameter is called the head diameter. DH. Now, how we can identify a rivet? So rivets are identified from its shank diameter. Rivets are identified from the shank diameter. So here is the screenshot of IS 800 1984. So here we can see clause 8.9.2.1. Here it is written that the gross area of the rivet shall be taken as the cross-sectional area of the rivet hole. So first, nominal diameter, it is the diameter of the shank. Now, gross diameter, it is the diameter of the rivet hole. So for the bolts, we have a specific table for the hole diameter, bolt hole diameter. But for the rivets, we don't have this kind of tables. So here in this clause 8.9.3, what is written that if we have rivets which now whose nominal diameter is less than 25 mm, for that we should take 1.5 mm as clearance, and the rivets whose diameter is more than 25 mm, so for this we will take 2 mm. So here these things are written. So if someone says say we have a rivet of say like 20 mm, so it's the nominal diameter. So what will be the gross diameter of this rivet? What will be the gross diameter of this rivet? Tell me, what will be the gross diameter of the rivet? If the nominal diameter is 20 mm, what will be the gross diameter? Quickly. What will be? 20 mm. For 20 mm, we need the clearance of 1.5 mm. So gross diameter will be 20 plus 1.5. So 21.5 mm, right? If we have 26 mm rivet, so the gross diameter will be 26 plus 2. That means 28 mm. Okay. So now we know how this rivets look like. Now how this rivet connection is made. So if we have two members like it, so how to connect them using rivet. So in riveting, what we generally does, first we make a hole, put the rivet. So this is the rivet here. Now for these sections, what we do, we generally follow two processes. So there are riveting process. There are two kind of riveting process. One is hot riveting and another is cold riveting. So in hot riveting, what we generally do, we just apply heat in this portion, then we do hammering and we make this portion also permanent. And in cold wire riveting, we don't hit that portion by using the mechanical hammering. We seal that portion, or we make the joint permanent. So by this way, riveting is done. So from here, we can understand that riveting is a permanent kind of process, right? And we need to hammering here, so there might be a hell lot of noise produced there. Okay. Thirdly, we need skill, manpower, skill labors. So there are some advantages and some disadvantages of the rivet connection. So nowadays, what we will do, we so here there are some advantages and disadvantages of the rivet. So you can go through it. Like advantages: permanent in nature, cheaper in fabrication cost, and disadvantages: yes, high level of noise, uh, labor cost, skill labor, preheating necessary, all these things. So nowadays, this rivet thing, getting obsolete day by day. Still, we are doing riveting. I'm not saying that it get obsolete absolutely, but bolt is, getting more popular nowadays. Now come to that bolted kind connections. The second kind of connections, bolted connections. So what do we mean by say bolted connections? The connections which are made from the or using the bolt, connections which we made using the bolt. So here you can see here a beam column connections, okay, where bolts are used as a connector. Now, so before going detail into that bolted connection, so what we will do today, we will go into the bolted connection. Rivet part, actually, I have, visited the syllabus where that rivet part is less covered. So I just went through the rivet portion to have some completeness or to have some essence of this rivet connection, or how this rivet look like, or to solve the assignments of previous year or the current year. I will, if you will need them, so you can go through it. Now we will go through the bolted connections in detail, step by step. And our code IS 800 2007, that actually covers that bolted design of bolted and welded part. Okay. So now let's try to understand what we mean by say bolts, okay, and how these bolts are look like. Okay. Is my screen is visible? Can someone confirm? Yeah, okay, thank you. Okay, so now let's try to understand what actually do we mean by say bolt. So we all have come across the bolts, right? We all have seen bolts. सबने देखा होगा bolts, right? So bolts क्या है? Bolts का basically first, this portion we call the head of the bolt. So heads can be hexagonal, octagonal, based on the, if we need to tighten them from two sides. Now we have in bolts we have some portion where the thread is not there. Thread is not there. We call this portion as sank, right? And we have some portion here where the threads are there. Threads. So if we zoom that portion, what we can see? Yeah, this section is sort of like this. So there are threads. Now why these threads are required? These threads are required to accommodate the nut, right? To accommodate the nut. So basically bolt has two portions. In rivet we don't have that threaded part, but here we have the threaded part. So we have two different diameter. Look, here the diameter is different, and here the diameter should be different. More precisely, here the cross section will be different, here the cross section will be different. Now, so which diameter should we call the diameter of the bolt? Like for the case of rivet, we call that the shank diameter, the diameter of the rivet. Now for the bolt, in which diameter we can call the nominal diameter or the actual diameter? So for the bolted connections, the diameter of the shank, the diameter of the shank or the diameter of the unthreaded portion is called the diameter of the bolt, diameter of the sank. So here, the diameter of the sank will be considered as the diameter of the bolt. And generally, we have 5 mm to 36 mm bolts readily available, and these are designated at like this M16. That means it's a bolt whose nominal diameter or the sank diameter is 16 mm. Okay. Now, so what I said, the cross-sectional area will obviously differ from that root and this sank portion. So what will be the cross-sectional area of this section? We call it the cross-sectional area of bolt or the area of sank, SB, area of sank of bolt. So what will be that? Pi by 4 into d square. D, what is the D? That is the diameter of the sank. Now, here, so obviously for this part, sank portion, the area will be less. So here we call this area is net area of bolt or the root area of bolt. So our code says for this root part, you can take the cross-sectional area as 0.78 into pi by 4 into d square. Okay. So now we come to know that the dia of bolt is the measure of the size of the bolt, like dia of the sank of the rivet was the indicative of the size of the rivet. Here the dia of the sank is the indicative of the size of the sank, and we have two different sections, and these two different sections are most important cross sectional area. I will cover it, like when my shear plane is passing through root, or will my shear plane is passing through the sank. So these two parameters or the cross sectional area will come into play when we try to design them, or when we try to understand what is the load transfer mechanism using these bolted joints. Okay. Now, till now, yes, the bolt dia, from the bolt dia we can understand, yes, this is the size of the bolt. Now, how we can understand the strength of the bolt or the material, strength of the material of the bolt? So for this we have another parameter, like we call them grade or class of bolt, very important parameter of the bolt. So using that grade and class of bolts, we can find out the ultimate and the yield strength of the material of the bolt. The strength of the bolt, we know the strength of the plate like Fe 410. What will be the ultimate strength of this? 410 Newton per mm square. Now if I said, tell me what is the strength of this bolt, how we can understand what will be the strength of this bolt. So from this class or grade of bolts we can understand the strength. So the grade of bolts generally denoted by two digits, one before the decimal and one after the decimal. So before the decimal, that 4 indicates the 1/100th of the tensile strength of the bolt, 1/100th of the tensile strength of the bolt. Say if we have 4.6 grade of bolt, so what will be the FUB, the ultimate tensile strength of bolt? That will be equals to 100 into 4, that means 400 MPa or 400 Newton per mm square, right? Now the second part, zero point 0.6, that indicates the ratio of your ultimate yield strength to the ultimate strength. YB by FUB is equals to 0. Say here 6. So we have calculated the ultimate strength 400 MPa. So what will be our FUB? That will be 0 0.6 into 400. So that will comes as 240 MPa. So by this parameter, we call it the grade of bolt or the class of bolt. From there we can understand or we can come to know the strength of the material of this bolts. Okay, so for example if we have 8.8 grade bolts, now tell me, quickly tell me, what will be the value of FUB and what will be the value of FYB for 8.8 grade bolts? Tell me what will be the value. Quickly write it down in the chat box for this grade. Quickly. If we don't understand clearly uh, how this strength we have to calculate with respect to the bolt, we cannot actually design that thing. Yes, yes, 800. Very good. 800. So what will be the no, what will be the yield strength? YB. You said FUB will be 800 ampere. Very good. What will be the FUB? It will be 800 multiplied by zero point 0.8. That means 640 ampere. So now we know how one bolt is categorized based on the diameter, and how we can find out the strength of the bolt. From the class of the bolt we can find out the strength of the bolt. Now this strength or the grade of the bolt vary from 3.6 to 12.9. Basically, when we design for the high strength bolt, that bolt, the class should be greater than 8.8. So I will come into it when I will cover the load transfer mechanism of the bolted joint. So till now we get some parameter of the bolt. We have some flavor of how these bolt are categorized. We don't have actually how these bolt are categorized with respect to the strength. We know, say grade 4.6, dia 24 mm. So we can find out, okay, we have to go for this bolt whose ultimate strength is that, whose yield strength is that. Now we need to design the rest of the things. Okay. So now very quickly come to this thing that we know the diameter of the bolt. For the rivets, that clause of IS 800 1984 says that there is two kind of diameter, one greater than 25, one is less than 25. For that you go for 1.5 mm if your rivet is less than 25 mm. If your rivet is more than 25 mm, then you go for the clearance 2 mm. But here for the bolt holes we have a dedicated tables. Okay, so to make a joint using bolts, what we need to do first, just say for example we have two plates and we need to lap them. What is lap, what is butt, I will come into later. So what we need to do is, first we make a hole, then what we will do, we insert the bolt and we will tight the nut here. Then obviously our connection happen. Now the thing is, what should be my diameter of this bolt hole? What should be that diameter of the bolt hole? How much clearance should I give? So for this we have sort of like standard clearances. For the most of the design purposes, we follow that standard clearances. That means diameter of bolt hole D0 should be equals to diameter of the shank or the nominal diameter of the bolt plus some clearance. That means we can easily put the bolt there. Or now think about it, this I just draw these two little sections. Now think about these big I sections. Now you have to put them using crane, align them, then put the bolts. If there are not enough clearances, then the life of that execution engineer will be suffered. Okay, so he will faces a lot of troubles regarding that alignment. So what should be that clearances? So we generally very often follow this standard clearance for the design of bolts. Now yes, these clearances have also meanings, I will tell you. So this standard clearance depends on the diameter of bolt. Like if we have 12 to 14 mm bolts, for that you need to go for 1 mm clearance. If we have 16 mm to 22 mm bolts, you need to go for 2 mm clearances. Like if someone says you have a bolt of 20 mm dia. Now tell me, what will be the diameter of bolt hole? What will be the diameter of bolt hole? So we have 20 mm dia bolts. What will be the diameter of that bolt hole? Yes, 22 mm. Very good. Because we are dealing with the standard clearances. So 20 plus, look, this clearance 2. That means 22 mm will be the size of the bolt hole. Now, these are the standard clearances. Now we have oversized clearance and slot clearances. Now, in oversized clearance, what we did, we give much clearances like this. Now, why we give this much clearances? When we discuss that load transfer mechanism of bolts, we will, come to know why this is things. So this is oversized and slots are look like this. This is short slots. Here the bolts are there, and this is called the long slot. Now why these slots and oversize are required? Just wait for, sometimes you will understand why these things are required. So now we have the understanding of bolt, the diameter of bolt, the strength of bolt. We have the understanding about the diameter of bolt hole and all these things. Now we have to know how we can place these bolts, or the way of load transfer mechanism. So now let's try to categorize the bolts based on the load transfer mechanism. So based on material, based on sizes, based on shapes, there can be different categorization. But with respect to designer, or with respect to design engineer, we need to categorize the bolt using, or based on the load transfer mechanism. Very important thing. So please pay attention in this part. This, load transfer mechanism, if you have clear understanding about how the load is transferred to bearing type bolt, how the load is transferred to frictional type bolts, then the design, the design procedure and the rest of the design class will be very easy for you. So first we will try to understand the bearing type of bolt, where in the bearing type of bolt, the load is being transferred by shear and bearing action. Now why I am saying that shear and bearing action? So here, same thing, I have two plates. I make some bolt hole here and put a bolt here, and I am applying the load. Okay, so for the bearing type of bolts, what we do, we just tight this nut up to a certain level, so that the members are firmly joined together. That means we are not introducing any kind of initial stresses, any kind of initial stresses. So this tightening condition is called snug tight condition. Snug, snug, snug tight. So in bearing type bolt, we go up to the snug tight condition. That means we don't introduce any kind of additional stresses to this bolt. Okay. So now I am applying the load. Just try to understand the phenomena. So applying the load, what will happen? Some certain time, this slippage will occur, and this slippage will occur, and this side, here you can see this side of the bolt come in contact with the plate, and this side of the bolt also come into contact with the plate, right? Yes or no? So when something touches something, what kind of stress is induced? What kind of? Tell me. Say if we draw the cross section over here. So tell me, if someone presses someone, or something presses something, then what kind of stresses is generated? Say it's the diameter of the bolt hole, or diameter of the bolt. What kind of stresses is induced? Bearing stresses. So here, when this plate is come contact with this bolt, the bearing will happen. The bearing stress will induce. The bearing stress will induce, right? Now, so here we can find out the value of bearing stress is P by D into T, the contact area. So bearing will happen here. Now one more phenomena will occur. What is happening here? If we see with respect to this plane we call shear plane. Now why we call this plane as shear plane, I will discuss it. Now in this plane, if we see, now this, just try to draw the cross section of the bolt. So this is the cross section of the bolt. Now tell me, this load P is acting in which direction to the cross section? It's a transverse direction. That means shear is induced. So what will happen? Either this bolt can fail in bearing or shear. So ultimately, this bolt, a bearing type bolt, is transferring the load through shearing and bearing action, right? Through shearing and bearing action. Now we just need to know what is the shear capacity of this bolt, what is the bearing capacity of the bolt, if that bolt is or can withstand the bearing stress or the shearing stress, whichever is induced due to the applied load. So these are the bearing type of bolt. So this type of bolts either can fail in bearing or it can fail in shear. So this plane is called the shear plane. Why? Because across this plane, what is happening in the bolt cross section? The stresses are shear stresses. So we have the shear stresses along this plane, and this can failure on with respect to this plane. So this plane we call the shear plane. Now come to the frictional type of bolt. In frictional type of bolt, what we generally do, say for example, we have three plates. Now we put a bolt and we tight the bolt up to certain level of pre-tension. Okay, say 0.5% of its yield strength. We just tied them. So what we did, we just put a tensile force or initial tensile force by means of any mechanical devices in this bolt. So what will happen in these two sections? The friction will occur, right? Just pressing each other. It's we have induced an initial tensile stress which produce the enough tension which can carry or which can transfer the load from one member to another member. So during this frictional action, the load is getting transferred. Now the thing is, I already told you that we have oversized holes, we have slot type of holes and long slots type of holes. So here for the frictional type of bolts, our intention is not to get in touch with the surface. Okay, so until or unless it will not get touch with the surface, the bearing or shearing effect will not occur. Only the friction thing will occur. Now, for this purpose of frictional type of bolts or high strength bolt, we generally go for the oversize or slot size holes depending on the design criteria. Okay, so now think a frictional type bolt, the slippage will occur and frictional type bolt will slip. So what will happen? It will act like a normal ordinary bolt. So in the frictional type of bolt, we have the load transfer mechanism based on the frictional action, and if slippage occurs, then that bolt will act like a normal bearing type of bolt. Okay, so these are the classification based on the load transfer mechanism. Now we'll go through it like bearing type of bolt, how to design the bearing type of bolt, what parameters should we consider design during the bearing type of bolt. What type of parameter? First thing we need to calculate the shear capacity, because bearing type of bolt are transferring the loads or supposed to transfer the load through bearing and shearing action. So now we have an idea that how a bolt is transferring the load. This idea is very much important because when we design the connections, we need to transfer some sort of loads or moments. So which kind of bolt should we use, or the bolt which I have used, should it be enough to withstand that load or not? Okay, now quickly go through some connections type. So type of bolted connections, let's quickly go through it. So based upon the arrangement of bolts. Firstly, we can categorize these bolted joints based on different parameters, like depending upon the arrangement of bolts, depending upon the arrangement of plates, depending upon the application of load, all these things. So let's quickly go through it one by one. So depending upon the arrangement of bolts, how we are arranging the bolts. So first we have the single line of bolting. Where? So here you can see this is the cross sectional view of two plates which are connected using the lap joint, and this is the top view or plan view where we can see the bolts. So here one line of bolting is used, so we call it single line of bolting. Where there are multiple line of boltings are there, we call the chain bolting. We have sort of zigzag or staggered bolting. So here this picture is the diamond building. Diamond building is also a kind of staggered building, we can say. So what are the advantages of diamond building over chain building? We will discuss when we will design this connector, this type of connections. Okay. In the next class, most possibly we will discuss these things. Okay. So now, based on arrangement of plates, we have lap joint. What is lap joint? When we need to lap two plates, then we call the lap joint. Now butt joint, in butt joint when we cannot lap the plates, okay, like many situations will occur when you cannot place the two sections, you know, lap in a lap position, so we have to go for the butt joint. So in butt joint what we do, we place the plates face to face, and we connect them using some cover plate. So this is called cover plate. So depending on the cover plate, we have two kind of bar joints, like single cover bar joints where one cover plate is there, and double cover bar joints where two cover plates are there. And sometimes we have packing plates. So you know, packing plates are for make the joint possible. They will not consider any kind of loads. So when we will design the bolted joints, we will go through that packing plate section also. Now, most importantly, based on the uh, location and nature of load, okay, how the load is transferred, or where we need to design the connection where this load is acting, like we can have the direct shear, we can have the eccentric loads, we can have some moments, all these things. So based on the location of the load, we have direct shear connection. Direct shear connection, that means the group of bolt is directly, you know, subjected to a direct shear. So here we can see this group of bolts is, if we put the load here, this group of bolt is directly subjected to direct shear. Why shear? Now we have already have the concept. Why shear? If you saw the cross section of the bolts, this load or stresses are on the transverse direction of this cross sectional area. So these all are the shear stresses. So we have direct shear connection. Now we have eccentric connections, right? So in eccentric connections, the load is not acting, you know, through the CG of the bolt. So here the load is acting somewhere else, but we need to transfer the load through that joint. So we call them eccentric connections, where due to the eccentricity, the load and one moment is generated. Okay. Now we have pure moment connections. When some couple is there, only moment is generated. And we have some direct tensile member, like we have a I section, and we need to you know, connect a T section using them, and here the load is applying. So for example, you have a, you know, flyover, that Kolkata flyover, and below that you need to, you know, make a, say, jhula. How you can make it? So it is sort of a direct tension connection. Now I will, you know, spend some time on this eccentric bolted connections. Okay, we will you know, spend a lot of time understanding this design process in the later due course. Then we will understand how to design them, how to arrange them, because this type of connections are most important connections in our design of steel structure, right? So let's quickly spend some time on that. Okay, quickly. So this is, we already said that if the load is not acting, you know, along or towards the CG of the group of bolt, the CG of the group of bolts. So if here we have 1 2 3 4 5 bolts are there, the group of bolt, the CG of group of bolts is this, but the load is acting here. So this type of connections, basically when the load of action of eccentric loading, or the line of action of eccentric loading, and the line of action of, or the line of group of bolts are on the same plane, we call them shear moment connection. Now why we call them shear moment connection, I will go into the. So for this load, eccentric load, what will happen to the CG of the bolt? One load will transfer and one eccentricity P into E. Say this is the eccentricity. So due to the direct load, direct shear will be, you know, induced in the bolt, applying direct shear will apply. And due to this moment, what will happen? Another force will generate here. Like due to this downward load, direct shear force will apply or generated in the bolt, and due to this moment one another force is developed, so F1 and F2. So we will discuss it later on when we will understand these things. So we call them shear moment connection when the line of application of load and the group of bolts are on the same plane. You can look at the both are on my the plane of my laptop screen. So here you can imagine this kind of connections here. Another is shear tension connection. It's also one kind of eccentric connection. Here what happened, here also due to that eccentric loading, one load is transferred to the group of the bolt, CG of the group of bolt, and one moment is generated here. So due to that moment, what will happen? Here we saw that due to that moment, one another force is generated. Now here due to that moment, what will happen? Just try to understand what will happen if we apply a moment here into it. What will happen? These bolts will get elongated. That means we will have tension on bolt, right? We will have the tension on bolt and a direct shear. So we have on the bolt direct shear and direct tension. Here we have direct shear and one another force due to moment. So if someone asks you, in a contradictory question, ki which kind of connection is this? Which kind of connection is this particularly? So what we will say? In a broader perspective, it's a shear moment connection. Now if we come to the design level, when we see the bolt level load transfer, it's a shear tension connection. Okay, so in a broader perspective it's a shear moment, but when we come into that thing, that what is happening towards the bolt or what is happening with the bolt, then we call them a shear tension connection. So if there is question where which kind of connection is this, go for shear moment connection. But if there is a shear tension connection available in options, go with that, because more precisely during these connections we need to consider the tensile strength of the bolt as well as the shear strength of the bolt. Okay, so basically we will design the connection on, I think, on third week of the course. Okay, so here I have put some glimpse of this type of connections. You can go through it. I will share this um, you know PPT. So let's quickly go through the failure mode. So if we want to design something safely, what we need to do is we have to understand what could be the possible mode of failure. Like if we need to design that pen, so at first I have to understand how this pen can fail. So it can fail from my hand, I can break it like this. So for designing also the steel structure or the joint, we need to understand how a bolted joint can fail. So tell me how a bolted joint can fail. So either the bolt can fail because my joint is made up from plates and bolts, only two things. One is steel section, one is the fastener. So either the bolt can fail, agreed, or the plate can fail, right? There are plate. If that plate fails, our connection will fail. So two kind of failure can occur. One where the bolt can fail, again when the plate can fail. So bolt can fail in shear because we are dealing with the bearing type of bolt. We are not talking about the frictional type of bolt. Frictional type of bolt will also be covered, but now we are sticking to the bearing type of bolt. So now recall that load transfer mechanism. How this bearing type of bolts will transfer the loads? Through shearing and bearing action. So either bolt can fail in shear, bolt can fail in bearing, and where the direct tension member, like I have said, we have a T-beam, we need to join them like this. So here the bolts are directly subjected to tension. So we need to consider these three failures. Now I will come that failure mode of failure one by one. And the plate also can failure. The bearing failure of plate can occur, the tensile failure of plate can occur, and the block shear failure of the plate can occur. So now quickly revisit that things, how the shear failure can occur. So we know when the slip occur, this two portion, this portion and this portion will come into contact with this plate, and here across this plane we will have a shear plane. So if this bolt is subjected to a factored shear stress which is more than the shear capacity of the bolt, that means, say for example, if that bolt can withstand 25 kilonewton of shear capacity and my applied load is say more than that, say 30 kilonewton or 35 kilonewton, so what will happen? It will break in shear. And here this is associated with one shear plane, so this we call single shear failure. So what will be the shear stress? The value of load and the area, cross-sectional area of the bolt. Now here that I have said that ASB and ANB, net area and gross area of the bolt, these two things come into picture. If we put a shear plane through that NB portion, 0.78 pi by 4 into d square. So stress formula, what do you know? Stress is equals to force upon area. The force is constant. If we reduce the area, the induced stress will be more. So the net portion will be our critical portion. So we have to, very conscious about where my shear plane is passing through. So if there is only one shear plane, we call it a single shear failure. If there is two shear plane, like we can say it here, we have two shear planes, and it can fail any of these two shear planes. So we can say it double shear failure. And if we have that multiple shear planes, so in there we have multiple shear failures. Okay, so this all about the shear failure of bolts. Now come to the bearing failure portion. Bearing failure, because our bearing type of bolt transfer the load using shearing and bearing action, right? So that bearing type of bolts, in failure of bearing type of bolts, what happens? Okay, so now here we consider three plates. So when we apply the load, what will happen? Slip will occur, because we are dealing with the bearing type of bolts. So where we just tightening them to the snug tight condition. So here this portion will come into contact, here this portion will come into contact, and here this portion will come into contact, and some bearing stress will develop, like P by dt. If D and T is the cross sectional area, so obviously the load divided by the contact area will be the bearing force. So if the bearing stress is more than the strength of this material, then what happened? The bolt will get eroded, and subsequently the failure. So this kind of failures you have, I think you have seen, so that hand pump, if you saw that hand pump portion, the bolt in the top of the hand pump get failed in bearing. So this type of failure occur when when we put some weaker bolt or less strength of bolt in between the stronger plates. Okay, so this is the bearing failure. Now what we have, another one is the tension failure. In tension failure, what will happen? If the tensile capacity is less than the factor tensile load which is applied on this bolt, so that bolt section will fail in tension. Now let's quickly come to the plate portion. So plate also will fail in bearing. How? Nothing. If we put some strong bolts within some weaker plates, so obviously the plate section will get crushed and it will fail. Now shear tear out, here what we have, if we don't provide certain end distances, then it will get there will be stress concentration in the hole and it will get crack out. And the tension failure or the rupture failure, so in the rupture failure, when we make some bolt holes, so what happened here, what happened in this cross section, we just reduce the cross section. That means if we reduce the cross section, stresses will increase. So if the stresses will increase, that portion will tear out. Now we have the block shear failure. Particularly when we design the tension member, this kind of failure occur. Or we can say when the shear and tensile force both are acting, then there might be a probability or possibility, if we don't provide the edge and end distances properly, then the block will come. So this also can be a failure. So one bolted joint can either fail when bolt will fail and when the plate will fail. So now we have idea, while designing that sections, we need to make sure that, if we need to transfer that amount of load, that amount of load should be safely carried by the bolts whichever I have provided, and the met plates or the sections whichever I have provided during the design. Okay, so these are the mode of failure of the bolted joints. Now we need to understand some terminologies, okay, before going to that problem solving session. So we have some terminologies regarding that, uh, regarding bolts. Like if we have here, we have a connections, like, so here we have a lap connections where a chain bolting is there, where three rows of boltings are there. There are two kind of distances you can see. There are center to center distance between this, and there are center to center distance between these two distances are there. Even there are this distance and this distance. So how to define this section, or what type of these distances are called. So first, pitch distance. What do you call the pitch distance? It is the distance between center of two adjacent bolt hole measured along the direction of applied load. Now think, what is the direction of applied load? This is the direction of applied load. So center to center distance between these two consecutive, or these two consecutive bolt holes are known as pitch distance. Now why this pitch distance are important? So we have to maintain some minimum pitch distances, because to avoid that bearing failure of plate. If we reduce the pitch distances, what will happen? The bearing failure of plate will occur. So our code says that minimum pitch distance should be 2.5 d, where d is the diameter of the bolt. Maximum pitch, for this we have clause 10.2.3, where that maximum pitch, like for the tension member 16T or 300, whichever is less; for compression member 12T or 200, whichever is less; and for direct shear, all these things. And T is the thickness of thinner plate. Now gauge distance. What is that gauge distance? It is the distance between center of two consecutive bolts measured perpendicular to the direction of applied load. Perpendicular to the direction. So direction of applied load this, and this is the perpendicular direction. So this is the gauge distance. Okay. So here the maximum gauge distance are also provided. Now two more things we need to quickly go through, that is end distances and edge distances. So end distance. So end distance is the distance of the bolt hole to the nearest edge measured along the direction of applied load or direction of applied stress. We call the end distance. And again, the distance between, or the distance from the center of the bolt to the adjacent edge measured perpendicular direction of the applied load, we call is edge distance. Now this edge and end distances play in vital role when our like shear tear out, block shear failure, to avoid this kind of thing. So code says a minimum value of these edge and end distances should be maintained during this process. So that should be for 1.5 d0, that should not be less than, this is for uh, machine cutted or mechanical cutted things. And we have one more things, 1.7 d0 for hand cutted or flame cutted or on site things. So d0 here, d0 is the dia of bolt hole. Okay, so till now what we have understand about the steel structure is, like, in steel structure this is made up with steel. There we just need to focus on the connections. The sections are readily available. In connections we come across the rivet one. We have some flavor what the rivet thing is, or the rivet thing does. Then the bolted one. Okay, now on the later classes, on the or the next week classes, we will learn how to design a bolted connection, or how to make a shear connection, how to make a direct shear connection, how to make a eccentric connection, how to design them, how to analyze them. So uh, up to now we will stop here, and now we will solve the previous year questions. So till now, if you have any queries, you can write it down, or quickly we solve the previous year questions, then we will open for the question and answer sessions. Okay, so now we have this is previous year question of the course design of steel structure. It's a 2022 question paper. So first question says, what does ISRO 80. 80 stands in ISRO 80. Tell me, write it down quickly. I just explained these things. The round section, the square sections, on all these things. So what does that means? That means we have an Indian standard round section of diameter 80 mm, right? So it's the diameter of the round section, right? Now, next question. What does ISST stand for? ISST. It's Indian Standard Strip Sections. Okay, tell me. In strip section, which two dimensions are defined? ST and SH. SH is for seat section. Why B? Steel seat sections. ST is the strip sections. I have already, you know, shown you the codes, right? So I'll let me go through that slide a little bit. Yes. In this slide you can see, and also I have add some screenshot for these sections. Okay, so here you can see that as per this code we have generally three seat sections, flat sections actually. So firstly we tell the ISSH, right? That is Indian Standard Seat section, and ST, that is Indian Standard Strip sections, okay, of the strip, okay, and of the seat. So for the seat section, seat, where we need to specify the length of the seat. So Indian Standard Seat sections are specified by its length, width and thickness, but the strip sections are specified using only width and thickness. And one more thing I have already said, that we have one more section, ISF, Indian Standard Flat Plates. Generally these are small width plates. So ISF is denoted using ISF, say for example 200 into 20. That means we have a Indian Standard Flat Plate sections of width 200 mm and thickness 20 mm. Okay, so what will be the answer of that question? What was the answer? Will it be Indian Standard Seat section or strip section? So it will be Indian Standard ST, stand for strip sections. Now come to next question. Okay, stainless steel is manufactured by adding foreign materials like like C, zinc and chromium. Very good. Because we have already seen that for the stainless steel material, you can refer the slide also. I have already said there high strength, high carbon steel and the foreign materials. Now, let's go to the next question. Yeah, zinc and chromium. Now, here the question is, due to uneven heating and cooling during manufacturing process of structural steel, which stress is generated? Which stress is generated? Yes, someone says residual stress. Yes, what do we mean by say residual stress? Like, yes, yes, it's the residual stress. So what is that residual stress? So like we have a plate, okay. If we, unevenly here we hit him, or if we have a thickness, larger thickness, hit them. So what will happen? Some distortion will occur due to that residual stress. Now, next question. इंक्रीज इन कार्बन कंटेंट ऑफ स्टील विल रिजल्ट. क्या करेगा कार्बन कंटेंट अगर बढ़ाएंगे तो? हम लोगों ने बात किया कार्बन कंटेंट के ऊपर. सो कार्बन कंटेंट अगर बढ़ाएंगे तो स्ट्रेंथ तो इंक्रीज होगा, राइट? बट साथ ही साथ क्या हो जाएगा? आवर डक्टिलिटी विल रिड्यूस. सो these two. Great. Now come to next question. Okay, so what should be the maximum permissible lateral deflection for the case of interstory drift in a building of story height 3 meter? So what should be the interstory drift? Actually, I will show you the code. Yeah. that portion, I think here. Okay, so this code portion is not, I am forget to attach here, so I will attach them. So generally what happened for the interstory drift, we generally consider the deflection limit as the story height divided by 300 mm. Story height divided by 300 mm. Okay, so here the story height is 3 meter. So we can convert it into millimeter. So we will get the answer. Now, okay. Here, in case of staggered pitching, pitch may be increased by, okay. I forgot to tell about the staggered pitching, right? Only I tell about only one type of pitching. So staggered pitching, that means in a staggered bolting, like if we have some sort of diamond bolting, so this called the staggered pitch. So for the staggered pitching, we can increase the pitch by 50%. So here this clause of IS 800 says that for the staggered pitching, it may be increased by 50%. Now, next, oh, it's a stress strain curve. Okay, so what that question says, consider a typical stress strain curve of steel structure. What will be the portion of D? This portion. What do you call this D portion? What do you call it? Strain hardening. Very good, Bhumi. And what this portion is called? CD. What this CD portion called? D portion is called strain hardening. Very good, very good. But now I am saying what this called? Softening. Yeah, we call this yield plateau point. Okay, yield plateau. Yes. No, not necking actually. We call them yield plateau. Necking will occur after this point. So this point is called yield plateau. And this D and E part, we call it the strain hardening part. Okay, so here in this slide, I have explained these things, and also in the NPTEL material, you will get these things. It's a basic things. Now, tell me, the center to center distance of adjacent rivet or bolt hole measured in the direction of stress. What do you call? In the direction of stress. In the direction of stress. Yes, yes, pitch. In the direction of stress, we call it pitch. Or in the direction perpendicular. Perpendicular, if I call perpendicular, say if I have this kind of connections, yes, perpendicular, we call them gauge, right? So if the direction of this load or stress, we call it pitch. Perpendicular, we call it gauge. Very good, very good. Now, according to IS 800 2007, what should be the partial factor of safety? Whose material resistance governed by yielding? Look, we have already discussed. We considered two kind of failure stages in steel structure. One is yielding, one is rupture. So we have to consider the factor of safety with respect to yielding. We have to consider the factor of safety with respect to rupture. So with respect to yielding, what should be the factor of safety for the material? You will get it in table 5. What is the value? Quickly. What is the value? Yeah, not 1.5. Here, the resistance governed by yielding is 1.1. 1.5, the factor of safety is not there. So 1.1, and if the resistance governed by ultimate strength, it's 1.25. So what will be the correct answer? 1.1. So for yielding, 1.1, because yielding, like, it's more safe than rupture. Like फट गया, पूरा टूट गया, और yielding के बाद भी कुछ सह सकता है. Understand this thought process? Okay. So the answer will be 1.1. Clear? Next. Okay. Now this is the load. क्या बोला है? Dead load, reaction load. So what will be that? So let's go to the code. So here we have dead load and that reaction load. So what is the value? 1.2 and 1.2. So what will be the correct answer? C. Now tell me, according to IS 800 2007, what should be the diameter of bolt hole if the diameter of bolt is 22 mm? Quickly. Yes, 24. Why? 22 is the diameter plus 2 mm standard clearance. Standard clearance. Okay. So 24 mm. We are not dealing with the oversize and slot size clearances when we design the bearing type of bolts. We only deal with type of holes when we design or we go for that high strength bolts. Okay. Now next question. क्या बोला है? Rivet connection has the following advantages. क्या advantages है? Rivet connection is permanent in nature, right? Rivet connection has high maintenance cost. This is the disadvantage. Rivet connection has cheaper fabrication cost. Yes, this is quite cheaper. तो इन दोनों ऑप्शंस करेक्ट है. अभी देखो यहाँ पे कौन सा है, 1 and 3, 1 and 3. C is correct answer. So here I put these things. You can go through it. Now calculate the nominal diameter of rivet. Is the gross diameter is 28 mm. Gross diameter, they said it. Gross diameter is 28 mm. And gross diameter of rivet is called the diameter of full. So what is said? Greater than 25 mm of rivets. I have added this slide. You can go through it. The clearances should be 2 mm. So what do we need to do? 28 minus 2. So 26 mm will be the nominal diameter of the rivet. So what will be the answer? 26 mm. Clear? If I said, say if the diameter of rivet is 18 mm. Now tell me what should be this is the gross diameter, 18 mm. Now tell me what will be the nominal diameter of the rivet? Quickly. Yeah, 16.5. Right, very good. So 18 minus 1.5. Why 1.5? Code says below 25 mm of rivets. For that, we have to consider the clearance as 1.5 mm. Now come to that question. Tell me which kind of connection is this? Quickly. I have explained you already. Which kind of connection is this? Yeah, it's a direct shear. Why direct shear? Why direct shear? Why moment shear? It's a pure moment connection. The couple is acting here, here and here. Only the couple is acting here. So it's a pure moment connection. I already have shown to you. It's a pure moment. Now, if this portion is not there and only P is there, then we call it a eccentric connection. And more precisely, if we go and dig into it, so if we have this kind of connections, like if we have the connections here with the bolts and gusset plate here, what do we call it? Shear moment. Okay. Now, the reduction in area due to bolt hole can be minimized. कैसे minimize कर सकते हैं? Like if we have a chain bolting, now it's a conceptual thing. I will tell you in the next class today. Time doesn't permit it. So, like instead of doing this chain bolting, I am using the staggered or diamond bolting. So using the staggered and diamond bolting, the cross-sectional area of the plate can be reduced. So if we have the cross-section here for the chain bolting, so here the cross-sectional area is less. Then what do we have the cross-sectional area here? So the cross-sectional area or reduction in cross-sectional area can be achieved through arranging bolts in zigzag manner, or more precisely in diamond facing. So diamond facing has huge added advantages. I will come into it later. So that's all from now from my side. So if you have any questions, you can ask me. Okay. So do you have any questions? You can ask me. Or else we can conclude here and we will, meet on next class. So actually I am unmuting you all. So you can actually, if you have any questions, you can ask me directly. Yeah. Now you can unmute your microphone and or you can raise your hand, and yeah, I will share the notes. NPTEL team will share these notes already and also these recording videos. And the first part, I can understand the first part of the video, you will face some trouble. So next class and onward, I will make sure that that kind of troubles will not happen. So now you can unmute yourself and ask questions. No problem. You are feel free to ask. Okay, please go ahead. You don't have any questions? Anything? Anything like so? Most of you understood what I try to cover today's lecture, or how this session will go on, and I need some feedback from your end how we can improve these sessions, right? So how we can improve the session, or how can we interact the sessions more in an efficient way, so that you can learn the subject. These subjects are very interesting subjects. If you spend time, if you try to understand them, these are the very uh, interesting subjects. Okay, so yeah, if you have any questions regarding that or regarding anything, so you can ask me. Go ahead, no problem. Anything.
So,
Yeah, Varun.
so will the codes will be provided during the final test?
No, actually, what NPTEL does, NPTEL does not allow that code, but the values are provided in the questions. Whatever values from the code you required, that values will be provided in your question only. Okay. So don't try to think about code is provided or not, but all the data which is necessary to doing some question, that all things will be provided in your questions. But make sure from the next class and onward, you should carry IS 800, SP6 and calculator before coming to this interaction session, so that you can uh, understand, and more interactively you can get what I am trying to say. No, you cannot use code in the exam hall, but the values or the uh, mm, that things, clauses, whatever is needed, that will be provided in the question. Okay. Anyone else? So most of you are undergrad students, right? Okay. So thank you. We will meet next Monday. Good night. Any formula will ask in exam? No. Generally, the formulas they don't ask the formulas. It's a sort of concept. Design is not about asking the formulas. Design is all about the concepts, the outcomes. So they will not ask the formulas from direct from the codes. They will not. Okay, so don't think about it. Okay, so good night. Thank you. Thank you.